So let's talk about today's learning outcomes. Today we're going to learn about divide and conquer. Divide and conquer is a very general strategy. You'll see it again and again and again throughout your years as a computer science student. We'll be looking at two particular versions of this strategy, which is binary search and merge sort. And then we'll be analyzing the performance of these using the techniques that we learned last week. Okay? Okay, so in the last lecture we talked about how we can get a list of the customers ordered by their purchasing spend. So basically we sorted the array, right? So today I'm going to start off with giving you a different problem. So the problem is just an extension of the last week's problem, which is that we want to find customer spending between two numbers, let's say A and B, where B is bigger than A. Alright, so between this bound. We assume that the data is in the customers array. And the array is already sorted by customer spend. So we used the technique last week to sort it, let's say. And Homer, who's our company mascot, and he proposed a very simple algorithm, which is this. Number one, we're going to find the start customer, basically the customer who spent A. And then the end is where the index of the customer who spent B. And then we're just going to print out all the customers from A to B. Okay, very simple algorithm for solving this problem. Okay, so that's what he proposes. So the key problem here, of course, is how to do this find index, right? This is trivial, but how do you find index of the customer who spent A amount of dollars? How do you find index of the customer who spent B amount of dollars? Okay, so that's the key question that we have. So if the array is unsorted, right? So how fast can you find the customer who spent $8 in an unsorted array? So you have no information about what's in the array, which I just give you an array. How fast can you find the customer who spent $8? So is it A, n log n, B, O n, C, O n squared, or D, O 1? So let's put your answer in onto poll everywhere. This is a warm-up, so it should be quite straightforward how to solve this problem.
No, it's with technician. You can put like that. O1 brother, O1 Why you don't have funny question again?
Okay, so more with 22.
O(n) square.
Most people are saying O(n), a couple of people saying O(n) squared. Maybe one person saying O1. Oh, that's changing. Yeah, wait till we get to 40. Okay, so put in your results, your answer. 34. Are we stabilizing at 34? Submission? Okay, so most people have put in O(n), some people have put O(n) squared, and O1. So the right answer is O(n), right? Why O(n)? O(n) because you have to do linear search, right? So if you want to find the customer who spent $8, you are not given any information about this particular array. The only thing you can do is really look one by one. Right, look one by one in the array until you find the person who spent $8, and then you just have to put it in. Okay, so this is in an unsorted array. The array is unsorted. But our array in our problem is sorted. All right, our array is already sorted. So I give you a already sorted array. I want you to find the index of the person who spent $8. Okay. So because our array is sorted, we will exploit this fact. We will exploit it. Exploiting structure or order in a particular data structure is a very common strategy in computer science. Okay, we will use it a lot throughout the entire semester. You will see us exploiting some sort of information that is inherent in the data structure. So here, if your array is already sorted, then there's something more you can do because you can use this information. So here's the idea. All right. Here's the question: if your array is already sorted, all right, and AI, also sorted in ascending order, all right. If AI is, I want to find 11. That's what I want to do. I want to find 11. All right. If AI, this is AI here, this is 7, is less than 11, do you search to the left or right or why? You search to the right. You know that everything on this side is going to be less than 7. less than or equal to 7. So you can throw it away. Right? You know it's not. You know 11 is more than 7. You can throw away everything on this side of the array. So now we can repeat this process. So let's say get the midpoint of the remaining array, and then you ask yourself the same question. Okay, 17 here. Is 11 smaller or larger than 17? It's smaller, right? So what part of the array can I throw away? On the right side, right? I can throw everything from 17 onwards because I know that I'm looking for 11. So I throw that away. Now I'm left with 8, 9, and 11. I look at 9. Again, which part do I need to check? The right side or the left side? The right side. Okay, and then I found 11. Right? So at each point, I'm exploiting the fact, instead of having to do an entire linear search, you notice I'm not checking every number in my array anymore. I'm being quite clever about which numbers I'm picking in order to find out where 11 is. So this algorithm called binary search is a very, very famous algorithm, okay, binary search. And this is the pseudocode, all right, for binary search. It does what you expect, right? You first set low, let's say low is 0, high is n minus 1. Okay, imagine this is your array A, right? And then you're going to go through from low equals high, you're going to get the middle point, right? The middle point is just low plus high divided by 2. And you check, right? If the key is less than the middle point, right, then you're going to reset your high value. So you're going to set your high value to 1 less than the middle point. Okay, because you know the middle point isn't the right answer, you've got less. If it's bigger then you set it to the low to 1, plus, the middle point plus 1, right, let's say on the right side. And if not, you found the answer, right? You found the answer, then you just return the value. If you finish, if this while loop exits, right, low becomes higher than high, then you return not found. It means the key is not anywhere in this particular array. Alright, so that's the idea behind binary search. You can work through it slowly, but the key point is just what we talked about, right? You're just throwing away part of your array at each time step, okay, each time you check out. Okay, so the first thing you might ask is, okay, is this code correct? Alright, we've been focusing very much on computational performance, right, before this. We talked about how the bound, the order of growth, right? How long does your computation take in order to finish the problem, to solve the problem? But we haven't really focused on whether your algorithm is correct. And you really want to make sure that your algorithm is correct. There's no point getting an O1 algorithm that is wrong, right? I can definitely give you that, right? That's not hard. We want to get a fast algorithm that is correct. Okay. So, how do you find out whether an algorithm is correct or not? That's the question we ask. So one way is by using what we call pre and post conditions and invariances. Okay, so we'll talk about that. So what's a pre and post condition? A precondition is a condition that is true before some set of operations, okay, a loop or a function. So that's what it is. Just something that has to be true before the execution of that piece of code. A post condition is something that's true after. Alright, so something has changed between the precondition and the post condition. Okay, so that's what you specify. This is very often specified in software engineering frameworks. Also when we're developing functions. It's called programming contract. Right? Why is it programming contract? What it says is this: if you guarantee me that these conditions are true before let's say my function, I can guarantee you that these conditions will be true after. Right? So it's like an if else. So it's contract, right? You give me this, I give you that. Alright? That's contract. So this is what it looks like. It's like there's a program flow, there's a precondition here. As long as the precondition is satisfied, there's some code where there's going to be something called an invariant. We'll talk about that in a second. And then there's some post condition after the code. Right? So that's what it practically looks like. So what is an invariant? Now, invariant is just a condition that is true during. Right? So we have precondition, which is before, post condition, which is after. Invariant is during. Some statement that is true during the execution of the program. Okay? And there's a special kind of invariant called a loop invariant. A loop invariant is just a condition that is true at each iteration of the loop. Okay, that is before and after the loop. That's what you have to check. Okay? So to check whether binary search is correct, we need to establish three main properties. Okay, one, initialization, that we set up our invariant correctly. Preservation, that the invariant is true at every iteration, right? So before and after. And when the loop terminates, then the desired result is true. Right? So let's look at a concrete example to make this more understandable. Right? But that's the basic idea. This type of technique was popularized in this book, actually, programming pearls by John Bentley. He does this thing to his students in CMU. So I think it's like not only CMU but also for seasoned software engineers. He gets them inside and he says, please code up binary search. Binary search is one of the first kind of algorithms that you learn, right? Like, for example, in CS2040S. And he codes them up. And invariably, most of the people code it up wrongly, right? And then he shows them this technique in order to get them to think about and code it up properly, right? So even students or seasoned software engineers will get binary search wrong if they don't think about it carefully. Okay, we'll look at that later. Okay, so let's look at this and talk about this, how you can set this up, how you can set up the preconditions, post conditions, and the invariances. Right. So let's talk about preconditions. So I provide, let's say you're supposed to write this function, binary search, right? The code that we have. I want to set up some preconditions, right? That the user has to guarantee before calling binary search. Okay, and then I want to then set up some post conditions. So what preconditions might apply here? Sorry? It's not empty array, okay. What else? Yes, A must be sorted, right? Because I said before that A must be sorted. If A is not sorted, then binary search won't work. Alright, so A must be sorted. What else? Related to non-empty array. So if I put N here, how are they related? How is it related to A? Okay, yeah, but more precisely, what does N tell you about A? It's the size, right? It's the size of it. Good. So here's it's going to appear everything by once. Okay, let's talk about post conditions first. So what do I want after? After I run my piece of code, okay, what do I want to guarantee my user? The guy calling this function. What do I guarantee? Sorry? The answer that exists, yeah, is where? Where is the, what am I returning? What am I giving? What do I guarantee? So where is, what does binary search do? The index, right? So make should be the index of where the element is in the A, right? Or, what happens if the thing is not in the array? What does this function do? It's not found, right? Okay, so these are preconditions. A is of size n, right? A is sorted, it's just 2, alright? You can put more, alright? I'm just coming with 2. And post conditions is the key must be in A mid or key is not found, right? So this is game programming contract. You set up I say these are the preconditions. You give me the preconditions. I give you the post conditions. Okay. So what's the loop invariant in this case? So there is a loop in this function. Right? This is the loop. This is the while loop. Right? There is a particular. How do you set up the loop invariant? Now the loop invariant is something that we want to be true throughout the execution. Okay? And the loop invariant often encodes the main logic behind binary search, behind the algorithm. Okay? In this case, it's binary search. So what is the key idea behind binary search? What are we doing when we say we can shave off part of the array? So what is the idea there? We maintain 2 bounds. And what is true about the 2 bounds? We maintain a low and a high. The key is in between. Great. So we're saying the key must be inside, right? If the key exists anywhere in the array, it must be inside between low and high. Right? If it's in the array somewhere, it must be between low and high. And then we're going to be working to maintain this property that is always between low and high. So this is what we want, right? A low, the key must be in between these 2. Okay? If the key is in the array itself. If the key is not in the array, then we don't guarantee this. Okay? This is the case. This is the loop invariant. So the strategy here is to work through the loop and consider each case. Alright? So let's try this out. Okay? So I want you to talk to your friend, alright, next to you, and try to work this out. I'll give you a couple of minutes for this. It's not very hard. It's just tedious. Okay, it's just tedious, but it's not very hard. So what you want to do is this. I'll start you off. In the initialization step, low equals to 0, high equals to n minus 1. Alright, that's the size of the whole array. Alright? In this case, is the loop invariant true? Is the key between low and high? Yeah. Of course, trivially is true, right? If the key exists in the array, it must be between the bounds, right? That's trivially true. Okay. Now let's work through each step, right, and show that it's true throughout the execution of this loop So at the first stage, low is bigger than high. That is definitely true. You get the midpoint. You get somewhere in between. Now you check, right? If key is less than a-mid, what happens? If key is bigger than a-mid, what happens? And if not, then you return it. Alright, so check out these two properties first because this will create a loop. This will not. Okay, so why don't you check that out? Then we'll talk about it in a couple minutes. Okay?
Only point I see is not the floor division. I don't think give you a floor, I give you a double. That's the only problem I can see. High equals to mid minus 1. Wow, I fucking confused. Fucking insane. So it's well, almost. I don't know. Wait, why is it correct? Mid minus 1. Okay, wait, makes sense. Yeah, mid minus 1, low plus 1. floor division, yeah. Return middle. Maybe I have a pseudo code on this homework. This homework is pseudo code. You would try PS1 maybe? No, I haven't opened. Oh, I think PS0 is a warm out. How you do the honest? Yeah. Yeah. Wait, what more is it? Common sense. What's the honest one called? Is it judging moves? I don't know that. I know what I do. I don't even remember what I do really. Yes, sorted.
Okay, time's up. Okay, so time's up. Let's talk about this and work through it together. It's not very hard, again, just a little bit tedious, okay? So let's look at these conditions one by one. You have low, high, and then you have medium, the mid point, right? So let's take the first if. So this is the first if, right? So if the key is less than whatever is in the midpoint, then I'm going to move my high value to here, right? N minus 1. New high, basically I'm going to shave off this part. Right? So, in this particular situation, is this loop invariant still true? Once you do it, is it true? Yes, it must be true. It must be true because the array is sorted. Right? It must be the case that the key must be in this zone. Right? So let's look at the other condition. If key is bigger than a-mid, low is mid plus 1, so I'm going to move low here. Right? Again, I'm going to shave off this part. Right? Is the key there? Is the loop invariant true? It must be true, again, because the array is sorted. Right? So this part is true. Okay? That's good. We show that at each, if not, then this loop will break. Right? If this happens to be the key, then we break. Okay, we return the value. So in this case, yeah, we've shown that each time the loop iterates, this is going to be true. Right? The loop invariant holds. So at loop termination, A is either the key or it's not off. Right? So that's the termination condition. Right? Is the design condition true? Again, yes, it is true. Right? This thing will only terminate here if a-mid equals to the key. Right? Or this condition happens, you can check it out slowly. This condition happens when you've exhausted your search, essentially. And then you will return not found. So this loop termination condition is also true. Okay? So you ensure that your post condition holds. So that's essentially what we've done. We set up the invariant. So in the initialization step, we talk you through, that sets up the loop invariant. The preservation step, the invariant is true at every iteration. Right? Every iteration, the loop invariant is maintained. And at termination, then your desired result is true. So it's very much like setting up your inductive proof, if you will. Right? You set up your base cases, and then you show that it's true at every step, and then the end is true as well. Okay, so that's how we set it up. So in this case, binary search is correct, almost. Okay, and we'll talk about why binary search is not exactly correct in this particular setup in a second. Okay, so how fast is binary search? When you put your answer, is it O log n, O n squared, or O1? So let's have a look. Next. Okay, so what do you want? Worst case by the way. So what do you think? Log n, O n squared, or O1?
Oh, they learn this well, teaching some kids or some complexity. You think what you want to teach what? Too much. Yeah, it's like over here all these like, maybe this is the first new thing that we learn. Loop in favor.
So the best case time complexity for binary search, what is it? Best case. What's the best case you think of? What's the worst case? Okay, so most people are putting in O log n. One person is putting O n, another person puts O1. Alright, so let's have a look. Let's have a look at what the answer is, right? So the right answer is ta-da, O log n. Alright? So the big question is why? Why is it O log n? Right? It's not enough to know what the answer is, but you have to prove it to yourself. So here's the question I started off with. In each iteration, you're shaving off part of the array. Right? You're shaving off part of the array. You're saying, I don't need to search that part, I don't need to search this part. So how much of the array are we shaving off, essentially? Okay? So at iteration 1, we have the array size is n. At the end of iteration 1 and iteration 2, we're going to shave off half of it. Right? So it will become n over 2. At iteration 3, we would have shaved off even more. It will become n over 4. And it will keep going on until there's only one element left. Right? In the worst case, we have to search through all the way until there's only one element left. Right? In the best case, what happens? If you're really, really lucky, the first one you hit is the key. Right? That's the best case. Right? So it takes a while. But that's really the best case. You have to be really super lucky for that to happen. This is the worst case where you have to go through all the way until you have one element remaining. Alright, so let's try this out. If you have, if this is the formula, right, n over 2 to the power k, you can see this evolution, right, to the 1, to the 2, all the way to the k, and we want to set up this equation where n divided by 2 to the power of k equals to 1. So if this is true, what is k in terms of n? Is it k to 2 to the power of n, 2 over n log n, or dmi in CS or math? So let's have a look. So we did this last week. So it should be, okay.
Now the double degree people who see.
So did you guys know that when CS is a relatively young discipline, right? It's a relatively young discipline. Mathematics has been around for a very, very long time. A lot of times when CS was first originated, it often originated in either the math or sometimes the physics departments. So that's where CS kind of built very much as a subdiscipline
why the
of
base
mathematics.
doesn't matter in
And then it
complexity,
grew from there, right?
change of
It's become
base.
this huge discipline that we know of today. But yes, a lot of the fundamentals of computer science is in mathematics. Discrete mathematics. Okay, so most people have put C, log n, and some have put MIC as math. Maybe some people have both. Okay, so this is easy to see, right? So if n over 2k equals to 1, then you know n equals to 2k. You just bring your k over. Yeah. You log both sides.
No, log n is equal to k.
No, log 2.
Then you get k log 2 equals to log n. And you know that log 2 is 1, right? So k equals to log n.
1?
Log 2, base 2 is 1.
Okay? Oh, that reminds me, whenever I use logs, very often I'm going to mean log 2, okay, log base 2. Alright, it's very common in computer science to use log to the base 2, not log 10, which we maybe see in other classes, or log to base e, which is in other classes. Right? So in our class, very often when I use log, it's log to the base 2. Alright? Okay, so the right answer, of course, is log n. Right? Each iteration takes c time, so it's just going to be the time complexity is going to be c log n, which is O log n, which is what you should know already from last week. What's the difference? So this is plotting out n, linear time, versus log n. You can see there's a tremendous difference, right? So last week we covered quadratic, which is curves up like this. This is linear, and this is something. This is log n, right? Logarithmic time. So we like logarithmic time algorithms. Logarithmic time algorithms are very, very efficient. All right. So whenever you can come with a logarithmic time algorithm, of course you can't always, but if you can, then it's fantastic. Okay. So what's the worst case space complexity for binary search? Okay. So not time complexity anymore, space complexity. Is it n log n, O n, O1, or kill me now? So.
Space complexity is O n.
So n log n, O n, O1, or kill me now. A lot of students are saying kill me now. Okay, space complexity. So space complexity means how much memory is it using? Okay. So, space complexity, when we talk about space complexity, we often mean not how much memory is, how to say, we mean usually how much memory is allocated during the execution of the code. Okay? How much new memory is created during the execution. Not how much memory there is, but how much new memory is allocated for the function in code.
There's no recursion, no nothing, just O1.
Okay, so let me... Anybody want to change your answer based on what I said? You can change your answer. It's okay. We allow changing your answers here. Alright, so we have a few. N log n, O n, O1, and kill me now. So the winner, the highest is O n, then kill me now, followed by O1. So let's have a look. So what's the right answer? The right answer is O1. Why O1? So some of you said O n. I'm presuming you say ON because you're thinking that, the array has n elements. Is that true? Is that what you're thinking? Okay. So you don't count that. Why don't you count that? You count that because A is provided to your function. A already has the memory allocated. You're not allocating new memory as a result of your algorithm. That memory is already pre-allocated. Okay, so you don't count that. You only count memory which you create. So if, for example, I created a buffer and I copied everything from A into the buffer, then yes, that's ON. Okay? But here I'm not creating anything new. I'm only creating a fixed number of variables. Low, high, mid. This is basically actually low, high, mid. Those are three. It doesn't matter how much n is. I always just create three variables. Alright? That's why it's O1. Alright, constant is bounded by a constant. Constant in this case is just 3. Okay? So it's bounded by a constant, that's why it's O1 for this problem.
I think the next people don't really care.
Alright, so let's take the top of the stack and look at the high level what we're doing. What we're doing is called divide and conquer, as I mentioned before. There are 3 steps to divide and conquer. Okay, so if you forget everything else, remember these are the 3 steps that strategy that you apply. One is to split your problem into little sub-problems. Okay? And you're going to solve each problem recursively, sub-problem recursively. And then you're going to combine them to produce the solution to the original problem. Okay, so that's the general idea for dividing. And it really is the basis of many kinds of efficient algorithms. So let's go back to our initial problem. Okay? So remember we talked about find index. So here, let's look at Homer's code. Homer's code is, I want to remember the goal, right? The goal is to find customer spending, the customers who are spending between $A and $B. Okay? And the array is already sorted by customer spend. So Homer's code is, again, find the start index, so the customer will spend A, N is the customer will spend B, and then we print all the customers in between. Okay, so what is the worst case time complexity for the algorithm on the left? Alright, if we use binary search for find index, right? Is it A, N log N, B, O, N, C, O1, or D, feed me, I'm so hungry?
Wait, if you
Okay, let's put in your answers here. It's either O, N, log N, O, N, O1, or feed me, I'm hungry. You guys get to eat before coming here? Out of curiosity. How many people get to eat?
ON.
I got to eat. How many people got to eat? Few? Okay. So the rest of you, I presume you're coming from other classes?
Yes, ON.
Don't get to eat. Okay. I don't, okay.
No, it's definitely not N log N.
Hence why D is so high. Okay.
ON.
Next time I'm going to explicitly request for non-lunch hour periods.
Fucking far like that.
I didn't make that constraint explicit when I was telling them.
Yeah, let it go. I suddenly remember it. Suddenly remember.
Okay, so we have ON log N, ON, the largest number seems to be ON. Some people are very hungry, and no one's picking O1, which is a good thing. Okay, so let's look at the result, the answer. So the answer is ON. So why ON, right? Why ON? So can anyone want to share why, for those who picked ON, why did you pick ON? The for loop. Okay. So let's take it step by step. When you're analyzing code, it's very important, or analyzing algorithm, let's look at things step